So this time I'm going to be talking about a simple question mark exercise predicting the next word. So basically we are going to try to perform a prediction task using neural networks, one that's a little bit more complex than the one that we did for the previous class, which was text classification task. And while we're doing it, I want to kind of go through all of the basics that you need to get a neural network model working properly. So it will give you all the kind of basic tools that you will be using in many of the neural network models that you would be creating. So in the last class, I did the example of asking whether all of these sentences are okay. As you remember, Jane went to the store to Jane went etc., like this. And basically, what we would like to do is we'd like to create a model that decides whether these sentences look like natural sentences that you're likely to see in a particular language. And specifically, this is called a language model. So calculating the probability of a sentence is a good proxy for deciding whether a sentence is natural or not. And basically what we mean by this is given a sentence X, we'll call our sentence X, we calculate the probability of the sentence. And according to, and we'll assume that big X consists of lots of little x's, which are the words in the sentence, or maybe the characters in the sentence. And using the chain rule, we basically, or for conditional probabilities, we can basically divide up P of big X into multiplying together the probability of the next word, given all of the previous words that we've seen, next word given context. So the this is interesting, and I think this is perhaps the most interesting problem, or maybe one of the most difficult problems in language, which is saying, does this look like natural, language in the target language that we're interested in, like English or whatever else? And in a way, it's very encouraging that according to basic rules of probability, we can divide the problem of calculating the probability of a full sentence into the probability of predicting the next word multiple times and multiplying them together. But the big problem is, how do we predict the probability over a next word, and what kind of model can we use to do this? So I will, to give a slight aside, there is an actual direct application for this, which is things like grammatical error correction or detecting how fluent sentences or discourses are. And one of the very strongest baselines or models for this right now is simply a language model with kind of slight adjustments made to make sure that you don't overly penalize rare words, for example. So basically, if you can train a really good language model, you can do a really good job of judging whether a sentence that somebody wrote is good or not. Is good, like grammatical or not. So to give a little bit of review, because one of the prerequisites of the class is that you have a basic knowledge of NLP, I think this will be a review for most people, but I'm going to very briefly go over count-based language models, which will lead up to the description of neural language models. And to give a little bit of background, actually, I started NLP before neural models came out. And when neural models came out, I was very, very skeptical about them, actually, despite the fact that I was still young and I shouldn't be skeptical about things. And, But I was skeptical about them because I was like, I don't know what's going on inside these models. And one of the reasons that really convinced me that neural models were a good thing to do is because I knew about count-based language models and could map neural models onto solving all of the problems that you can see in count-based language models. And I'll try to explain the reasoning behind this in this lecture. So count-based language models, basically what they do, they're also known as n-gram language models, but basically what you do is you count up the frequency of certain word strings and divide to get the conditional probability according to the standard equation for maximum likelihood estimation. So if you look at the equation here, basically what you can see is in order to calculate the probability of the next word, we add up the frequency of all the previous words in our context. In this case, we're using a context length of n words, and the next word, and divide it by the frequency of the context itself. So as you probably learned in algorithms for NLP or in another NLP class that you've taken, the problem with this is that this is not robust to when you have 0 counts for any particular sequence of words. So, like for example, if you had I went to Pittsburgh to visit Carnegie Mellon or something like that. If you've seen, I went to Pittsburgh to visit UPMC, but you never had I went to Pittsburgh to visit Carnegie Mellon. Even though these are extremely similar sentences, you would still get a 0 probability for them because the count of I went to Pittsburgh to visit Carnegie would be 0. So the way we do this in count-based language models is we add smoothing to deal with the 0 counts. So basically what we do is we gradually and recursively fall back to shorter contexts that which allows us to deal with this. So you make your context shorter and shorter and shorter until you get context that you've seen before. And one of the kind of typical things for this in one of the assignments in algorithm for NLP is to implement this. But modified Kneser-Nye smoothing has a whole bunch of kind of tricks that make the smoothing work really well. And that made it, up until very recently, a very strong baseline for n-gram language modeling. Also for language models, the important thing is once you have a language model, how do you tell whether it's a good language model or not? The answer to this can be, is that we have evaluation measures for language models. The most standard evaluation measure for a language model is the log likelihood of an entire corpus. So you, this is not the most standard, but this is one very straightforward one. And basically, you have a test corpus that isn't included in your training data, and you add up the log probability of all of the sentences in the training corpus. You can also divide this by the number of words in the corpus, and this is good because then if you have different sized corpora, you can kind of compare the values across the different sized corpora. And there's also cross entropy. So cross entropy is basically the negative log. Often it's measured in bits, so negative log 2 of the probability, and also divided per word. Per word log likelihood, higher is better. Per word entropy, lower is better. And as I talked about last class, when we're training neural networks, a loss function generally is something that we want to decrease or minimize. So cross entropy is a very common loss function used in the training of neural networks as well. And then there's also perplexity, which is 2 to the entropy, if we're defining entropy to be log 2 of the probability, or e to the negative word log likelihood like this. So basically, perplexity follows directly from these per word log likelihoods and per word cross entropies. And I think there's 2 reasons why people use perplexity. The first reason why people use perplexity is there's a pretty straightforward interpretation, which is if you randomly guessed the next word according to the next probability distribution, how many times would you need to guess before you get it correct? So if your entropy is, if your perplexity is 100, and then you told your model, please predict the next word, that would mean you would have to guess about 100 times before you got the correct answer on average. Another reason why people use perplexity is the number is bigger than the like 0.1 like 2.5 entropy, and if you have bigger numbers and they decrease a whole lot, your paper gets accepted more often. So, yeah. So anyway, this was hopefully just a refresher for most people. The next question is what could we do with language models? Why are we interested in them in the first place? I think from a philosophical standpoint, language models are a very nice task. Because basically what language models are doing is they're saying, are you able to model the probability distribution of data, of language data? And if you're able to model the probability distribution of language data, philosophically that kind of means you know something about the language. You know what kind of sentences are likely, what kind of sentences are unlikely. So it's kind of a very straightforward task that nonetheless has a lot of complexity and is kind of interesting. From a more practical standpoint, you can use it to score sentences. So for example, I gave the example before that you could use this for grammatical error correction, where you have a number of potential ways that you could modify a sentence to fix things, and then score them with a language model and present the best one. Another thing you could do is if you have some system that outputs like lots of different possibilities to generate text, like let's say you had a dialogue system or a machine translation system, you could then use a big language model to rescore them to get the most natural one out of the lot. Another thing that you can do is directly generate sentences from them. So the way you can do this is basically you step gradually through the sentence and you generate the next word. And then based on the words that you've already generated, you pick the probability of the next word and you get random like sentences according to the language model probability distribution. And this is a good way to inquire into the model and see what it thinks is kind of like a natural sentence in that language. So this is a kind of an overview of language modeling. Are there any things that people would like me to clarify or elaborate on? No? Okay. So now what I mentioned before is that one of the reasons why I really got interested in neural networks is I saw that they were a really good tool to fix the problems that we had with, for example, n-gram language models. And n-gram language models do have a lot of really big conceptual problems. One of their biggest conceptual problems is they're not able to share the strength among similar words. So for example, she bought a car, she purchased a car, and she bought a bicycle, and she purchased a bicycle. Here, the bought and purchased are basically synonyms, so they should be interchangeable in most contexts. Bicycle and car are things of similar classes, so they should appear in similar contexts. But the problem is that normal n-gram models just memorize exactly the surface kind of statistics, so bought and purchased aren't sharing any parameters whatsoever. So a solution for this in the n-gram model literature is class-based language models, where you turn things into classes and you decompose the probabilities according to these classes. You also cannot condition on context with intervening words. So for example, if you'd seen Dr. Jane Smith before, in your model, if you suddenly got a less common name like Gertrude, you would not be able to share the fact that you'd seen Dr. Jane Smith to calculate the probability next. There was actually a method called the skipgram language model that far preceded the skipgram that maybe people in this room know now. Now, kind of, if you hear skipgram, you think of word2vec, or a lot of people will think of word2vec. But skipgram language models were basically language models that ignored a word and just conditioned on the previous words. And then finally, one very widely cited problem with n-gram language models is n-gram language models have a limited context, so they cannot handle long distance dependencies. So for example, if you had 4 tennis class, you wanted to buy his own something, you would know it would have to be something relevant to tennis, right? And then if you had 4 programming class, he wanted to buy his own something, you would know it had to be something relevant to programming. And because of the nature of language, where you can make long phrases, kind of arbitrarily long phrases, it's really important to handle these accurately, and n-gram models aren't able to do this with the limited context they have. And there were a bunch of different kind of methods to solve this, including cache models, trigger models, topic models, syntactic language models, etc. So actually, I think because people before neural networks were smart, they knew what their problems were, and they came up with all of these special purpose solutions to solve them. And there's this huge paper of about 120 pages. It's a technical report from Harvard by Joshua Goodman. It's called A Bit of Progress in Language Modeling. And this is actually a pun because the bit of progress in language modeling, the word a little bit, but it's also a bit of entropy. So he incorporated all of these things. He was an amazing implementer, implemented all of these things and combined them all together. And eventually he was able to improve language modeling ability by 1 bit of entropy. And his final conclusion in the paper is, this is so depressing. You have to implement all of these things, and it's so hard to actually make any progress in this task. This task is over. We shouldn't do it anymore. So, and honestly, like after reading that paper, I was like, yeah, I don't want to do that. I don't want to go in and implement all of these things just to make a little bit of progress on language modeling. So I think that's one of the really nice things about neural networks is, as you'll see as I step through all of these things, they give a really elegant solution to solve all of these problems that would have been harder to solve in other frameworks. So first, to start out, I will give something that's not exactly, it's not a neural network per se, but brings us closer and closer to a neural network. And I'll explain how it solves some of the problems that we had before. So I'm going to talk about featurized models, and featurized models calculate the probability in a different way. Basically what they do is they calculate features of the context, and based on the features, they calculate probabilities. So you optimize the feature weights using gradient descent or some other method. And to give an example, let's say in this case, we have a limited context, and the limited context is a 2-word context. And we want to extract features from this and use them to calculate the probability of the next word. All of the words that we're predicting are here on the left. We could be predicting, this is the vocabulary of the words we're predicting. It could be the, talk, gift, hat, and any number of other things. And what we do is we extract, we have feature weights for all of these. And basically, the first thing we have is a bias. And the bias basically tells us how likely are the words overall. So and the are very frequent words, so they'd have a very high bias. Then the next thing we have is a weight vector given that the previous word was a. So we have giving a, so a weight vector given the previous word was a. So given that the previous word was a, and the suddenly become much less likely, right? Because you don't have or the very much. But maybe things like nouns, like a talk, a gift, a hat would become more likely. And then finally, we have how likely are the words given that the second previous word was giving. And this is a little bit less clear. Maybe giving blank talk, giving blank hat, make talk and hat a little bit more likely. So this is kind of these are weights for this particular feature. And what we do is we add them all together to get total scores. So does this remind anyone of anything that we saw like last time? Any brave people to talk in front of the 90-person class?
When we had scores for each word for good to a very good to very bad. Mm-hmm. For a sentence, we used to add up all the scores and then kind of predict which.
Yep, exactly. So this is very, very similar to the bag of words model, right? We took a look at the previous words, and then we added the bias together. So what's different from that model? There's one kind of major difference with that model and this model. Any ideas? Yes.
There's a dependency on the context.
Yeah, there's a dependency on the context. A little bit more specifically. Yeah, position, yes. I had like three people say the same thing over here, so I don't know who it was. But we're conditioning on the position. So we have the previous position, the second previous position, et cetera. So these models, and then we take the softmax and convert this into a probability to get the probability. And this is the equation that I wrote on the board last time. But basically, we exponentiate the score and we normalize. And I think this is very familiar to a lot of people, but just in case it's not, the motivation isn't clear, the reason why we exponentiate is to make sure that everything is positive. The range of the exponent is from 0 to infinity. So this ensures that everything is positive, and then we normalize to ensure that everything adds up to 1. So what this ensures us is that every number in this distribution is between 0 and 1, and it adds up to 1. So this makes it a valid probability distribution. So to give an example, we take all our scores, we run them through this function, and we get something that looks like this for the probabilities. So actually, I don't know if people know this, but does anyone know Roni Rosenfeld from NLP? Yeah. So he actually invented these models. Back a long time ago, before he was doing flu forecasting or the stuff that he's doing now. But so the interesting thing here is we can also express this as a computation graph. We can create a computation graph where we have like lookup 2 for the previous word, lookup 1 for 2 words ago, and we take our bias and we add them all together, get our scores, run them through the softmax. So again, this is like exactly the same as the thing that we had with a bag of words, except now we have positional information in our lookup vectors. So a note here, when I say lookup, what exactly do I mean by a lookup? Basically, a lookup can be viewed as grabbing a single vector from a big matrix of word embeddings or parameters or something like this. And this is a really, really common operation that we'll do in almost any NLP model that we do. So what this does basically is this takes a matrix where the number of rows is equal to the number of words, the number of columns is equal to, the number of columns is equal to the number of words, the number of rows is equal to the size of the vector. And then if we do lookup 2, we maybe grab the second column from this. There's a close parallel to this, which is, this can be viewed as a multiplication with a one-hot vector. And what a one-hot vector is basically a vector where all of the numbers are 0, one of the numbers is 1, and we multiply these together, and we get a vector. And mathematically, these are exactly the same. Does anyone have an idea of like why we might choose the first or might choose the second? Yeah. Maybe matrix stuff is easy to do. So like one example of where it would be easy to do is like if you had a library that only handled matrix operations or something like that. So yeah, that's one reason. Yeah.
I think the first is easier for the computer because they have a lot of multiplication with 0 involved with the second operation. Mm-hmm. So that's the stage.
So yeah. So the first one, if implemented correctly, can be less computationally, computationally faster. So in reality, I think in most neural network libraries that support NLP in any way whatsoever, which in reality is most neural network libraries nowadays, you have something like the first one where you look up things according to an index. That being said, the second thing is a nice thing to know because there are some kind of creative things that you can do with this. Like for example, what if this wasn't a one-hot vector? What if this was a different type of vector where you had 0, 0, 1, 0, 2, or something like that? And then you could implement, for example, a bag of words model where you first counted up the frequency of all of the words in the sentence and did it with a single matrix multiply. Or maybe you had some sort of probability distribution over words that you would want to use. So I think both of these views are important, but by default you would generally be using the first one. Yeah, so the former tends to be faster. So in order to train a model, we calculate a loss function. This is a measure of how bad our predictions are, and we want to move the parameters to reduce the loss. So we want to kind of reduce the badness of our predictions. The most common loss function in probabilistic models is negative log likelihood, and this is what is used to train, I don't know, like maybe 90% of neural models for whatever various tasks that you're interested in doing. There are plenty of alternative loss functions as well, but I think log likelihood shows up in many of them. So for example, let's say your correct answer was element number 3. You would take the third element or zero-indexed second element in this probability vector, and then you would take the negative log of this, and this would turn into your loss function. And most libraries actually, because this is a really, really common thing to do, most libraries will implement this select an element, take the negative log operation for you without you having to implement all of them yourself. So for the parameter update, by doing backpropagation, which I explained last time, this allows you to calculate the derivative of the loss with respect to the parameters. And then we can do an update of our parameters. The most simple update is stochastic gradient descent, or simple stochastic gradient descent. And simple stochastic gradient descent, basically what this does is it just subtracts this derivative multiplied by a learning rate alpha. And the intuition behind this is you basically want to move the parameters in the direction that would reduce the loss. So that's why you're subtracting. You want to reduce the loss, so you want to move in the direction that reduces it. This simple stochastic gradient descent is actually remarkably good. It's kind of a default that people have used for a very, very long time, but it still works very robustly, even with respect to training large models and stuff like this. It does have a few problems, which I'll talk about later. Are there any questions so far? Yeah.
So in the model that we just discussed, the weights and biases we're training there,
Mm-hmm.
and how does the position exactly play a role?
Oh, so how does the position play a role? So in this particular model, the way the position plays a role is essentially we have two of these matrices. We have essentially we have one for each position that we want to distinguish. So you can also think of a model where you had one matrix for the previous word, one matrix for the word before the previous word, and then another matrix for all the other words in the sentence, and then you don't actually care about their position. So you could also be creative, but basically anywhere where you want to make a distinction, you would have a different parameter vector there. And I'll talk about some alternatives using neural networks later also. Any other questions? Okay, so another important thing for language modeling, and actually just about any neural model for NLP, is how do you choose the vocabulary that you want to handle. And this is actually most important for language modeling, I think. And the reason why I think it's most important is because it actually affects the validity of your comparisons between models and other things like this. So one of the problems with models is unknown words. And unknown words, we don't have all the words in the world in our training data. And in order to do that, we will probably get some new words in any test set that we've never seen in our training set before. Another problem specifically very salient to neural nets is larger vocabularies. If we have a very large vocabulary of words, this will require more memory and computation time, so we'll need more parameters in our big parameter matrices. And also when we make our predictions over all the words in the vocabulary, and just calculating the values of the softmax takes a fair amount of time. So there are common ways to take some subset of the vocabulary that we have and turn the rest into unknown words to reduce our vocabulary size. One very common way to do this is any word that's only appeared once in our training corpus, or any word that's only appeared n times in our training corpus, or less than or equal to n times in our training corpus, we turn that into an unknown word and we remove it from our vocabulary. A second common way is using a rank threshold. So let's say you want a vocabulary of 50,000 words for whatever reason. You'll just create the vocabulary, count its frequency, and remove everything that isn't in the top 50,000 words. And as I said before, this is really, really important, particularly in language models, but also in other models as well. So if you want to compare language models, you must the vocabulary must be the same over the models that you compare. So the reason why this is like, let's say you, by creating an unknown word, effectively what you're doing is you're taking a vocabulary where you have like the, and it, and is, and then you set all the other words to be equal to unk. So here, and essentially you have a 5-class classification problem where you take the top 4 words as your actual vocabulary and you make everything else unk. And then you compare that with another one where you take the top 6 words or whatever. The, it, is, period, and I don't know, comma or something like that. And then you have unk here. And so if the vocabulary sizes are different, or even the vocabularies are different, even if the size is the same, basically you're solving different classification problems, so the difficulty of these is different. So you really can't compare the probabilities for language models across different vocabularies. So actually, there's a small caveat here. Like, for example, if you have a model that's based on characters, the model that's based on characters can generate any word whatsoever. And it is okay to compare a character-based model with a word-based model, as long as you don't ask your character-based model to generate all the unk words, where you're only asking your word-based model to predict the words that are in the vocabulary or unk or something like this. But if you're interested in this, you can ask me about the details. But just you have to be very aware of this. So I have a sample implementation of this, which I'll go through quickly. And basically, the way this works, especially because I had an example, I had a question about how you implement the different parameters. Basically, what you do is you have a set of parameters for each word in the range. So let's say n is a range of 2, you would have 2 of these parameters. And based on a history, you add the bias, and then you add you take the word ID and the parameters for that particular position, and then you append the score vector, and you sum them together. So I'm not going to go through the code examples in detail, in that much detail here, because I think it's not the best use of time. But if you want to go back, you can go back and take a look at this and see how you calculate the scores. So, are there any questions about the model itself? Yeah.
So in that coding example, the weight matrix size is number of fours times number of fours.
Yes.
Wouldn't that be too computationally expensive?
Wouldn't that be too computationally expensive? Computationally, no. Memory-wise, yes. And the reason why computationally no is actually precisely because of the thing that I talked about before, where if you're doing a kind of, and this is actually really important. This is really important when you're thinking about computational feasibility, but here you're just kind of looking up things at the top, and this is O of 1 in the size of the vocabulary. It's a constant time in the size of the vocabulary, but it is quadratic in the size of the vocabulary and parameter space. But if your parameter size is, if you have like 50,000 words in your vocabulary, what is that? That's two, or let's see, 100,000 would be, trying to add my zeros. 1,000 times 1,000 would be 1 million. So 10,000 times 10,000 would be 100 million. So it'd be 100 million parameters. Each one takes 4 bytes. So that's 400 megabytes. It's not infeasible to hold somewhere. So things that seem infeasible actually are, because our computers are powerful, you are actually able to do them. But I agree it isn't the best use of things. And the models that we do next is better. Will be better. Any other questions? Yeah.
So in terms of matching the vocabulary,
Mm-hmm.
other than extrapolating what words you regard as words and common words, are there any established practices of how you tokenize words in the first place, or how you process words, whether you look at case, or whether it's
This is a really, really good question, actually. So are there any established practices about how you tokenize words or turn them into, pre-process them in an appropriate way? And the answer is, I don't think there's any general established practices, but on the language modeling benchmarks that we have, generally people have already pre-processed the data for you. Unfortunately, this is not the case in some other things, like a task very near to my heart is machine translation. And in machine translation, this is actually a very serious problem. So much that there's a paper written about it. And the idea is basically people are reporting blue scores, reporting these scores, accuracy scores with different tokenizations, and they're not comparable. And if you actually change the tokenization, you get a different result for which model is the state of the art. So basically what they proposed here is an official kind of like standardized protocol for evaluating these things. But I don't think this necessarily exists for other tasks. So it's something very important to think about. Are there any other questions? Yeah.
What happens to tokens which are generated during test time? Like how are they scored? So
how are UNC tokens generated during test time? That is a very good question. In a standard word-based language model, there's no good way to do this. So basically what you will get is you'll get text with UNC tokens in it. There are better ways to do this in things like sequence models, where you take in a sequence and try to generate a sequence, but I'll talk about those then, so maybe I'll leave it until that time. But this is a really important thing also, because if you UNC most of your vocabulary, you're going to get text with lots of UNCs in it, which practically isn't very useful at all. But it would have low perplexity. So that's the problem with comparing things with different vocabularies. Okay. How did I turn into a slideshow? Hang on one second. So now I'll move on to the next thing. So I think you might have gotten a preview of my slides inadvertently. So then the question is, what problems are handled? So one really big problem that, or one problem that isn't handled is that we can't yet share strength among similar words. We still have this big n words by n words parameter matrix that was pointed out here. What we can do is we can condition on context with intervening words. So you saw the 2 words ago feature that we had, which allows us to do this. Long distance dependencies we can still not handle in the particular model that I introduced here because it was only conditioning on the previous two words. So next I'll move on to an actual neural network and moving on to a nonlinear model. So as I mentioned last time, linear models can't learn feature combinations. And for language modeling, this is something that's really important. So for example, I have an example here where the previous two words and the next word in particular combinations that aren't just single words actually have an influence on the output. So for example, farmers eat steak. This is probably pretty reasonable, so it should have a high probability. Cows eat steak should be low, I think, because cows don't normally eat steak. Farmers eat hay should be low, whereas cows eat hay should be high. So basically, what you'll note here is it's not just like you can't 100% say because farmer exists here, it would be high or low. But you can, like in the combination, you're able to figure out what things should be rational or not. So these kind of more complicated dependencies can't be expressed by linear features. So what can we do here? And one way you can do this, and this is actually the way that people did this before they started using neural network language models, is you actually remembered combinations of features. So you would remember things like the fact that farmers eat appeared, the fact that cows eat appeared, etc. But the problem with this is that the feature space basically explodes. And now we're not talking about n words times n words, but we're talking about n words times n words times n words. And that will not fit on your computer if you try to remember all those parameters. So we can turn to neural nets, which I mentioned are excellent feature combinations. Excellent ways to create feature combinations. So neural language models, basically the way they work is, the simplest one is a neural network classifier that takes in the two previous words and feeds them into nonlinearities and predicts the next word. So specifically, what does this look like? This looks like look up a word embedding for this word, look up a word embedding for this word, concatenate them together, multiply them through a nonlinearity, and this nonlinearity is able to extract feature combinations into this purple vector here, and then these feature combinations themselves are used to predict the next word. And then we can take the softmax and turn them into probabilities. So the good thing about this is, I mentioned the problem before with extracting, explicitly extracting feature combinations. As your parameter space explodes, you can't share features appropriately, and this causes you to not have enough memory to not be able to learn the parameters on a limited amount of data, etc. So the places where these allow you to be more parameter efficient is basically in these word embeddings here. And these word embeddings can be shared among all the input words. And this allows you to basically share strength among similar words in the input. And also, similar output words will get similar rows in this matrix of parameters here. So if words tend to appear in similar contexts, you could share the strength between these in the weight matrix that you have here. Also, similar contexts will get similar hidden states. So you can share information between contexts that similar contexts as well. So basically, the nice thing about using neural networks here is this allows you to share all this information and learn efficiently from your data. So now if we move on to our problems that we have, we can see that the neural networks are a good way to solve our problem of sharing strength among similar words. And also share strength among similar contexts. So if you have bought A and purchased A, these will get similar hidden vectors. So they can share information. And then car and bicycle, they're slightly different, but they might appear in similar contexts. So the word vectors for car and bicycle might also be similar. And I have an example, but in the interest of time, I won't show it here. You can go back and look at it if you'd like. But are there any questions about this? Okay. So another interesting thing that you can take a look at here is that we can actually note that the input words and the output words that we're calculating the probability of will be the same in many cases. So basically, if you remember, our lookup vector was this big, our lookup matrix was this big matrix of the number of words times the size of the hidden embedding. The output softmax matrix is also the number of words times the size of the hidden matrix, or sorry, size of the hidden vector here. So you can note that actually this parameter matrix and this parameter matrix will be the same. So it's actually common now to tie the parameters between the thing that you're using to calculate your input and the thing that you're using to calculate the probabilities. And the big advantage of doing this is actually in neural language models, these are the biggest parameter, the largest numbers of parameters that you have. So by tying these together, you reduce the number of parameters, you make your model easy to learn. So this is something that if you're creating any sort of model that generates, that's either a language model or a sequence model or something like this, something you should definitely try out. You can also try it in the code example if you'd like. That'd be not be too difficult. So this is a very simple language model that nonetheless can do lots of interesting things. But next, what I'm going to talk about is using this as an example, come up with a few training tricks that could be useful, not only could be useful, but are very largely essential for implementing these things well. So the first training trick, this is something that I actually talked about last time. This is something you should definitely be doing, is shuffling the training data every time you do an update. This is in all my code examples, and it's in all my code examples for a good reason. But basically, stochastic gradient descent, because it's gradually updating the parameters based on the last example it's seen, it's very heavily biased towards the previous examples that you've seen right at the end of training. So by shuffling the training corpus, so yeah, like if you have, I love this sentence so much at the end of the training data 50 times, your model will be very heavily biased towards basically classifying that correctly or classifying towards that label. So to train correctly, you randomly shuffle the order at each time step or at each epoch. So this is something that's basically essential and will almost always help improve your results. Other optimization options. So I talked about very simple stochastic gradient descent. But one of there's a couple problems with simple stochastic gradient descent. The biggest problem perhaps is that it's slow. There are much faster optimization options that can cause your model to converge 2 to 5 times faster, and because you're all impatient graduate students or undergrads or something like that, this is pretty attractive. It's very attractive to me also because I'm also impatient. The second problem is that stochastic gradient descent is very sensitive to the choice of the learning rate alpha that I talked about. So you need to be very careful about picking the correct one. So there's a couple of other options. The simplest possible one is SGD with momentum. And what this does is basically it remembers a few of or it keeps a track of kind of the rolling average of the previous updates that you've done. And what this does is this prevents stochastic gradient descent from kind of like jumping around a huge amount in various directions and kind of makes a more smooth curve when you're optimizing your model and causes it not to be as unstable at test time. Another option that people don't really use anymore, but kind of use very much anymore, but it was kind of started a move towards adaptive gradient methods, is called AdaGrad. And basically what this does is it adapts the learning rate to reduce the learning rate for frequently updated parameters. And the way they measure this is with the variance of the gradient. So there's a very, very intuitive explanation for this that's particularly salient to neural models for NLP, which is that some words are more common than others, right? So the words the and is, etc., will have their parameters updated really, really frequently, whereas rare words like Carnegie and melon will have their parameters updated not so frequently. So when you update the and is and you already have a pretty good idea about what those parameters should look like. But when you see Carnegie and melon, you kind of want to update them in a bold manner. That takes a big step in the parameter space to update them better. So that's the basic idea behind here. You can take a look at the actual equations if you'd like. And then finally, kind of still one of the standard go-to methods that people use is called ADAM. And it's like AdaGrad, but it also keeps a running average of the momentum and the gradient variance and does some additional adjustments and stuff like this. So there's also many, many other proposed methods, and most of them are implemented in some sort of neural network toolkit, so you can just use them. There's a very good reference that I have on the website. It's a blog post by Sebastian Reuter that kind of explains all the different methods and their differences and has some graphical illustrations, etc. So I won't go too much into the details here. The question is which one should I use? And the answer is usually just try Adam, and it will largely work for you. But if you really want to get the last tiny percentage of accuracy out of your model, it might be a hyperparameter that you would want to tune. Another thing that is very good and very useful for making your model training stable and causing and giving you better accuracy overall is early stopping. So in learning rate decay. So basically, neural networks have tons of parameters. They could fit the training data really, really well, but they're also prone to overfitting. And one way to prevent them from overfitting is we can monitor the performance on some held out development data that's not included in our training data. And when we stop training, when we start to do worse on this data. So basically, the way our training will usually work is our training loss will go down like this, more or less monotonically, and just continue going down. And then you have your loss measured on your development set. And at some point, this will start to get worse. And that's the point when you want to stop training and use the model that you found at that point. So practically, the way you implement this is every time you get the best development loss, you write out your model, and then you use the last model that you wrote out when you're actually testing your model. So then there's a question about which one to use. Adam is usually fast, convergent, stable, so I suggest it. There's an interesting paper at NIPS. It's also somewhat controversial, so you shouldn't take it entirely at face value. You should have maybe a bit of a grain of salt about it. But there's a paper examining the fact that SGD actually, if you let it train long enough and you choose its learning rate carefully, can outperform many of these adaptive gradient methods. So SGD, if you really, really want to get the best accuracy, SGD is something that you should try out as well. You should also try using learning rate decay. And basically what learning rate decay does, I skipped over that part. But what learning rate decay does is basically with some schedule, you start out with a higher learning rate and you gradually reduce your learning rate as time goes on. And for SGD, this is really, really important. SGD isn't proven to converge if you don't do this learning rate decay. But for things like Atom, they already kind of do this learning rate adjustment, so it's not quite as important, but it's still very beneficial. Especially a learning rate decay strategy. I have no idea why, but this learning rate decay strategy is called the Neubig strategy. Probably Bob came up with it, and Bob had an old strategy and a new strategy, so it's called the Neubig strategy. But basically, the way, what you do is you continue training, and then when you get to the point where the development loss is the best, you then resume training from this point, and you lower the learning rate. So your initial learning rate might be 0.1, but then once you get to this point, you resume with 0.05. And this, like if you lower the learning rate a bit, this causes it to be more stable and not overfit quite as much. So we have done experiments on like machine translation, and what I found on machine translation is kind of the best strategy is to use this together with this strategy of training until you overfit, then rolling back your model to here, and then continuing training with a lower learning rate. Together with Atom seems to work pretty well, converge quickly. But you know, this isn't the only answer. So I think there's just being aware of these techniques and trying them out on your problem is the best way to go. Are there any questions about like learning rates or optimizers or things like this? Yeah.
So for the Atom, does the learning rate was set at the beginning of the training still matters as it really does?
The learning rate, does the learning rate set at the beginning of training matter for Atom? And the answer is yes, it does, definitely. Atom has a global learning rate, but compared to SGD, it does quite well with the default learning rate of 0.001. But in many, many cases, I've seen people use slightly lower learning rates. I've seen people also occasionally use higher learning rates. So Atom, it's not the case that just because you have Atom, adjusting the learning rate will like not give you gains. Yeah.
So what is the intuition behind that the performance increases when using the Neubig strategy? So why does decreasing the learning rate when the model has trained the best with the previous learning rate increase performance?
So I kind of wish I had a better answer to this. Like my answer is not going to be very convincing, but there probably are papers examining this. But my intuition here is that kind of lower learning rates take less bold steps into space, and because they take less bold steps into space, they're less likely to strongly fit the training data, which means that they're also less likely to overfit and a little bit more cautious when they're moving through the parameter space. One thing that's for sure is lowering the learning rate causes less instability, and it causes you to fit the last examples less. So that might also be another reason why. There probably are papers about this, but I haven't read one, so I can't answer very well. Are there any other questions? Okay. So another thing, this is something that you need to have in your bag of tricks to use, dropout. So dropout, basically what it does is neural nets have tons of parameters and are prone to overfitting. And what dropout does is it randomly zeroes out nodes in the hidden layer or some other layer at training time with probability P at training time only. And so what this means is every single time you sample a different mask, and this mask is used to delete some of the nodes in the hidden layer. And the reason why this is supposedly useful is if you think about a really degenerate strategy where each training example gets its own hidden node, and you basically remember, like, this hidden node corresponds to this particular training example, you could fit the corpus, you could overfit the training corpus really easily by just, like remembering all the training examples. But what dropout does is basically it prevents you from doing this by every once in a while killing the node that you used to remember it last time. So you need to develop more robust features that prevent this from happening. And there's a bunch of there's also nicer theoretical interpretations of this, which is basically like you're creating an exponential number of ensembled models. So you're training an exponential number of models and combining their predictions together later. But you can take a look at the original dropout paper to learn more about that if you're interested. There's kind of two ways to do dropout. One way to do dropout is One important thing is because you're doing this only at training time only, this means that the scale of the parameters at training time will be different than the scale of the parameters at test time. So like, let's say on average you zero out half of the nodes in your hidden layer. That means the norm of the hidden layer, let's say the norm of the hidden layer is 20 in that case, or something like that. Let's say arbitrarily the norm of H is equal to 20 at training time when you're using dropout. But then at test time, because you're not dropping out half of the nodes, your norm at test time will be twice as big. So it'll be approximately equal to 40. And this is a big problem because basically, like, let's say you did this directly before your before the layer you were using to make your predictions. That would mean the scores that you get when you're doing dropout would be a lot smaller than the score in scale than the scores that you get when you're not doing dropout. So in order to fix this, what you need to do is either at test time, you basically multiply by your dropout probability. So if your dropout probability is 0.5, this reduces the scale to be equal to like what you had at training time. Or at training time, you can divide by the dropout probability, which gives you something similar to what you'll be seeing at test time. And how this is implemented depends on like what toolkit you're using, for example. But it's important to know which one you're using. I think most toolkits use this inverted dropout, which makes it easier to implement, and it's less error prone. There's also a bunch of other alternatives to dropout, but one notable one that I'd like to talk about is drop connect. And basically what drop connect does is instead of dropping out individual nodes in the hidden layer, it drops out weights in the weight matrix. So you're taking your big weight matrix and you're zeroing out random entries in the weight matrix. And this is used in kind of a state-of-the-art model that I'll talk about later. So I have another code example that you can take a look at to see this with all of the optimizations. The next thing that I want to talk about is not ways to make your model train better, get better accuracy, but rather be more efficient. And this is also something that's really important. It's also really annoying, but you have to do it, so I'm sorry. So basically, one of the efficiency tricks is mini batching. And what mini batching does, basically, is it combines together multiple operations usually over multiple training examples into a single operation. And this makes things much faster. So for example, on modern hardware, doing 10 operations of size 1 separately is much slower than doing one operation of size 10. And what I mean by this is, like, let's say we want to add together 10 digits. Writing a for loop that adds together those 10 digits is much slower than taking two vectors together and adding them. And the reason why is because, for example, on GPUs, if you have a GPU has many, many threads that are all running in parallel. And those many, many threads can calculate like 256 operations together in the same time that it would take for them to calculate one. On CPUs, you can do multi-threading where you use multiple CPUs to do things, but also CPUs have something called single instruction multiple data operations, SIMD operations, where basically you can calculate, you know, I don't know the exact number, but like 8 or 16 additions in a single CPU operation. So even on CPUs, this is very relevant. So because of this, what we would like to do is combine together smaller operations into one big one. So to give an example of how this works, basically, you know, in neural networks, one of the biggest things that we do is doing a matrix multiply via our parameter matrix, adding the bias and doing some sort of nonlinearity like a tanh. So what we do is we take our 3 data vectors, we concatenate them together into one big matrix. We do a big matrix-matrix multiply. In this big matrix-matrix multiply, we can do really quickly on GPUs or CPUs. And then we add a bias vector, and this bias vector does something called broadcasting, where you basically duplicate it along the columns. And what this does is this takes the let's see, we had 3 operations apiece, and we did each of them 3 times. So we have 9 operations. So instead of having 9 little operations, we have 3 big operations. The matrix multiply, the sum, and the tanh. So the way we do this manually, normally, is we group together similar operations. For example, loss calculations for a single word, and we execute them all together. In the case of things like a feed-forward language model, each word prediction in a sentence can be batched together because each word prediction is taking the previous words, you know, running them through a nonlinearity and calculating the next word. In the case of things like recurrent neural networks, which I'll talk about later, things become a little bit more complicated. So basically, you can't batch together things in different positions in the same sentence. You need to batch together like multiple sentences together. And for things like a tree structured model or things with more complicated structures, it becomes even more complicated. Exactly how you do this depends on the toolkit. A lot of toolkits like PyTorch or TensorFlow require you to add an extra dimension representing the batch size and concatenate your data together in stuff like this. Dynet, in particular, has a special mini batch operations for lookup and loss functions, and basically everything else is automatic. But I think the first one is more common, and it requires you to think kind of in higher dimensional tensors. So instead of thinking of a matrix, you think of a tensor of dimension 3, where one of the dimensions is your is kind of like your batch dimension. I'll skip that code example, but you can take a look at the code example here. So there's also a nice thing that you might want to consider using if you probably don't want to do this if you're thinking about just doing RNNs or language models over flat sequences. But if you're working with things like tree structures or things like this, batching actually takes a very large part of your time that you use for implementation. But there's a few libraries that allow you to basically automatically batch together operations. And the way they work, sorry, I had an animated GIF, but the animated GIF disappeared when I, the animated GIF disappeared when I turned it into a PDF. But the way basically this works is you, where's the GIF? So basically, what you do is you calculate each individual example that you're interested in processing separately, like you weren't doing batching, And then the neural network toolkit works behind the scenes to batch things together for you. So the reason why this is nice is basically you don't have to write batching code at all, and it goes in and batches things together for you. Some examples of this are auto batching in Dynet or fold in TensorFlow. So if you're using any of those, you can try them out. But basically the way it works is the engine automatically finds operations that are the same size and can thus be batched together and does all this batching for you. So the advantage of this, obviously, is that it's easy. The disadvantage of this is it is a little bit slower, or a fair amount slower in some cases, than batching things together yourself. But we did do some experiments that show that you can get a lot of the gain that you can get from manual batching with automatic batching. So this here is if you don't do any batching at all, and you can see that things are way slower, and this is why everybody has to do batching for neural networks. But if you automatically batch, you can reduce the amount of time that you need, and multiply the number of sentences that you can process in 1 second by 10 times or something like that. So might be something worth considering. Are there any questions about efficiency things? Yeah.
Is there any best practice for tuning the hyperparameters for individual researchers who have limited resources of computing?
Are there any best practices for tuning hyperparameters? That's a very, very good question. Long story short, if you don't have very many resources, usually the best thing is intuition. There's also a very famous method called GSD, which is graduate student descent. A graduate student gradually descends towards a good set of hyperparameters until their paper can be published. But
Ask specific, like computing semantic parsing, that field has.
Sorry, I'll give you a more serious answer next. So, a more serious answer is it's very good to look at previous papers that have done similar tasks and start from there. There are automatic methods for hyperparameter tuning. Some examples include grid search, where you search over a number of parameters. Also random search, where you just randomly, you pick the range that you want for your hyperparameters and then randomly select from them. Actually, people have found that random search, like even theoretically, random search is probably better than grid search if you have enough parameters. It doesn't feel very systematic to me though, so I don't use it very often, but that's another option. And then if you really want to kind of go deep into like methods that could automatically tune things for you, there are things like Bayesian optimization, which basically tries to fit the function of the scores that you would expect from particular hyperparameters. And there are libraries like, I think it's called Spearmint. That you can use for things like this. So long story short, I think almost all of the time people just go in and tune things themselves, especially in a university setting. But there are automatic methods to tune things like this as well. This was a very good question. Actually, all the questions today were great. Thank you. Are there any other questions? Yeah.
Back in the rebatching, after the operations with rebatching, why you contact mapping all the results after the operations instead of just sum it up or averaging?
Well, so if you're calculating something like, so the question was, why are you concatenating instead of summing them up? So in the very end of your computation graph, you usually have something like a loss function that you want to calculate and minimize. And at the very end of your computation graph, you will be summing that up or averaging it or something like that. But in the intermediate states, you need to still remember all of the hidden vectors that you have for a particular example or something like that. So you can't really do that summing or averaging until the very, very end. Yeah. Yeah.
Yeah, a quick follow-up for the first question. So are there any specific techniques for setting the batch size?
Are there any specific techniques for setting the batch size? So this is actually a really good question, and I want to clear up a very common misconception about mini batching. This is like really, really common, so I wouldn't be surprised if half the people in here have this. But one thing that people do is they try to set the batch size as large as possible for your GPU, for example. Like you try to set the batch size as large as you possibly can get on whatever computational hardware you have. But number one, this isn't always the best choice of a batch size. And number two, this isn't actually necessary to have limitations on your batch size based on how much fits into GPU memory. So number one, batch size is actually a hyperparameter that causes, that affects the stability of your training. So the bigger batch size will have you, so a bigger batch size will generally be faster if it fits on a single GPU or something like this. It will also be more stable, so it won't bounce around as much because you're doing updates for multiple examples at the same time. However, it will very often be slower to converge at the beginning because at the very beginning, you can calculate small batches. You can calculate small batches and do more updates per second. And at the very beginning, it actually doesn't matter if your batches are very small. You're still moving in the right direction. So another thing is very big batch sizes actually can cause you to fall into local optima at the beginning of training. So it's not uncommon for smaller batches to do better because the bigger batches kind of fall into these local optima more easily. There's actually a paper by Google Brain, I forget the exact name, but it's something like don't adjust learning rate, adjust batch size. And their recommendation there is you start out with small batch sizes and then you make bigger batch sizes as you go along in training to prevent overfitting and stuff. The second misconception is that if you can only fit a batch size of 32 on your GPU, that means that for the purpose of training, you only have a batch size of 32. But in reality, sometimes a larger batch size is better for training. Like it's more stable or something like that. So what you can do is instead of having a batch size of, let's say you wanted to have a batch size of 128, what you can do is you can make your batch size to fit on your GPU size 32, but then do 4 updates in a row or 4 gradient calculations in a row and accumulate them all together before doing an update. So I try to separate the idea of a computational batch size and a learning batch size. So the computational batch size is memory bound, but the learning batch size is not memory bound. So if you see Google with their 5,000 TPUs had a batch size of 128 or like 1024 or something, know that at least it is possible for you to reproduce their result, even if it would be like slower, I guess is the moral of this story. So because we're right at the end, we're right at the end, so let me finish this. So the final thing I have here is a case study. This is a paper from 2017 that now kind of is one of the state-of-the-art baselines that people use for language modeling. And basically what it did was it just tried a whole bunch of regularization strategies and optimization strategies for language modeling. And it uses LSTMs as a backbone, and we'll talk about these later. But to look at the tricks that they use to improve stability and prevent overfitting, they use things like drop connect regularization, SGD with averaging, where they start averaging when the model is close to convergence. They use dropout on recurrent connections and embeddings. They have weight tying between the input and output matrices. They also independently tune the embedding and hidden layer sizes. So they didn't necessarily make the embedding size equal to the hidden layer size. They also had regularization on the activations of the network. So this is a little bit unusual, but basically they have a loss function that tries to prefer small activations of the network. And this is kind of a strong baseline that a lot of people use for language models. But what I wanted to point out here is, number one, go and read this paper if you want to create a strong baseline. Number two, all of the things I talked about today, or many of the things I talked about today, are the things that go into these kind of state-of-the-art models. So yeah, I guess that's all I have. And I will take individual questions after class now because the class is over and I want to let people leave. But thank you very much.